I am Conor MacBride. I'm a solar physics PhD student at Queen's University Belfast in Northern Ireland. I'm doing a project on energy dissipation in solar physics with my supervisor, Dr. David Jess. But before that, I did my undergraduate at the University of St Andrews in Scotland. So MCALF is an open source Python package for accurately constraining velocity information from spectral imaging observations using machine learning techniques. So basically it's for measuring Doppler velocities in waves in the solar observations. So what the package would do is it would take a spectrum, it would classify that spectrum using any sort of classifier, whether it's machine learning or not. It will then adapt the fitting method that's applied to the spectrum based on the classification. So you can tune the sort of method or you can tune whatever function you're fitting to it. Once that's done, it will then fit the spectrum using that model. And then once it has fitted it, you can take the parameters that it's fitted and then generate other information such as velocities. So MCALF makes this particularly easy to do if you're doing this sort of thing, working with spectra, and there's different sort of stuff happening, and you want to be able to take into account more of the physics when you're fitting something. And it's also intended for people who have sort of more of a background with IDL, so that they can quickly get up and running with doing this sort of thing in Python, and they can then try more working, say, with NumPy and stuff and matplotlib, and not have to worry too much about like the whole structure of a program at that stage. So I'm leading the development along with my supervisor, Dr. David Jess. MCALF is available on GitHub. We also have a documentation website, and it's available on both pip and conda. So in this introductory presentation, I will outline the key method behind MCALF and discuss the other features of the package, as well as the various DevOps infrastructure that we are using. I will also show you a live demo of MCALF being applied to a real data set. Okay, so now in this section, I will go over the key method behind MCALF. This method was published in MacBride et al. 2020. To study dynamic events in the solar atmosphere, often observations with a high temporal resolution are required to be able to resolve the active phenomena such as shocks and jets. To achieve such high temporal resolution, often only spectral imaging observations are feasible. That is, only the Stokes IE parameter is recorded. I have been working with one such data set taken on the 30th of August 2014. With the interferometric bidimensional spectrometer known as IBIS. Co-aligned images from this dataset of calcium 8542 angstrom are shown along with the continuum image taken from the HMI instrument at the Solar Dynamics Observatory. When wave amplitudes in the chromosphere exceed the local sound speed, shocks are formed. Spectral lines such as the calcium 8542 line that I'm using are particularly temperature sensitive, so capture the shock and show it as optically thin emission in the blue wing of the calcium 8542 line spectra. To better understand the waves present in the solar atmosphere, these active emission spectral components need to be segregated from the underlying quiescent absorption spectral component. If these components can be segregated, Doppler velocities can be determined and used to study the waves present in the solar atmosphere for both the quiescent and the active regimes. So this is what MCALF will do. It will fit two profiles depending on whether these are in it, and then able to extract the various different parameters from that. So the software will segregate the two components by fitting two void profiles to each spectrum. The void function is a convolution of a Gaussian function and a Lorentzian function. This void function better models the broadening of the line profile, which occurs due to radiative transfer effects. Bounds are applied to each of the two void profiles such that one models the active emission component and the other models the quiescent absorption component. The central line core wavelength for each component can be extracted from the fitted parameters of each void profile. And by comparing them to the stationary line core wavelength of a previously generated average quiet sun spectral profile, Doppler shifts and therefore Doppler velocities can be measured. This method of fitting multiple profiles works well when multiple profiles are actually present in a spectrum. The dynamic events such as shocks do not affect all of the spectra in a dataset. Only some of the spectra will actually contain multiple spectral components, with the rest having only a quiescent absorption component. In spectra where there is no active component and only a quiescent absorption component, the additional flexibility introduced by the additional void profile resulted in the overfitting of the spectrum. This overfitting meant that the line core wavelength of the quiescent void profile did not represent the true line core wavelength of the quiescent spectral component because the overfitted active void profile was pushing it to the side. To overcome this challenge, we used machine learning, specifically a neural network classifier, to classify each spectrum depending on the level of emission present in the line profile. As you can see in the image, 5 classifications were chosen, with classification 0 showing purely absorption characteristics, with signs of emission starting at classification 2, continuing to classification 4, where the emission is considerably brighter than the continuum. The fitting method could then be adjusted depending on the assigned classification. Spectra which only contained a single component were fitted with a single void profile, while spectra that contained both a quiescent and an active component were fitted with the double void model. For this very simple neural network use case, we just used the multi-layer perceptron or MPL classifier provided by scikit-learn. However, any classifier object can be used with MCALF. Comparing classification 0 to the rest of the classifications, you can see that spectra of classification 0 are much smoother around the central line core compared to the rest. I was able to fit the spectra better by lowering the priority of precisely fitting the detail at the tip of the line core peak if the dataset was particularly noisy. I also lowered the priority of fitting out into the wings for all of the spectra, as we are only interested in the position of the line core. This way, I could focus on fitting the profile to the slopes and to determine the line core wavelengths accurately. The code can be applied to an entire field of view of our IBIS dataset, and therefore we can produce a velocity map as shown. The velocities in the plot on the left are calculated using the line core wavelength from the quiescent absorption component, while in the plot on the right, the velocities are calculated using the active emission component. Areas where the spectrum only contains an absorption component and therefore no active velocity was found are shown as a darker gray. By calculating a modified chi-squared statistic, we can see that the accuracy of the fit is very good. For each spectrum, the chi-squared value is calculated using the central 25 wavelength points out of 49 in total, with the chi-squared value then subsequently scaled by multiplying it by 49 over 25. This allows us to approximate how well the fit is performing around the line core, the region we are most interested in fitting. For this proof of concept study, we trained the neural network on a set of 100 labeled spectra and tested it on a set of 100 labeled spectra. Both of these sets were different. For this relatively simple neural network use case, we were able to achieve sufficiently high accuracy with only a small number of ground truth spectra. We trained the classifier to distinguish between 5 different classifications. However, when adjusting the fitting method, spectra of classifications 2, 3, and 4 are all adjusted the same. Therefore, we had in effect three groups of classifications, 0, 1, and 2 to 4. Within these three groups, our neural network performed very well. Its average precision was 91%, and its average recall was 90%. I'll briefly explain what precision and recall mean. To work out the precision of classification 1, for example, you would take all of the spectra that the neural network has labeled as classification 1, count the number of correct classifications, that is, the number of true positives, and divide it by the total number of positives. And then to work out the recall of classification 1, you would take all the spectra that should be labeled as classification 1, count the number of spectra correctly labeled by the neural network, that is the number of true positives, and then divide by the total, that is the number of true positives and false negatives. These are two key numbers when evaluating the performance of neural networks. We can prioritize increasing one value over the other, depending on the specific use case of a neural network, in effect, adjusting its sensitivity. We can regroup again and have the neural network detect either absorption or emission. Absorption is defined as classifications 0 to 1, and emission is defined as classifications 2 to 4. Now with these two groups, the precision and recall increased to 96% and 95% respectively. This shows that neural networks can provide a quick way to detect the location and spatial distribution of shocks in a spectral imaging dataset. This may also be useful to confirm that effects from active events such as shocks are not contained within a dataset. Future work could involve compiling a database of labeled spectra from various different spectral lines and instruments to enable neural networks to be quickly trained as needed for specific datasets. We could also investigate the accuracy of neural networks trained on simulated spectra, as we can set the classification of each simulated spectrum beforehand. Creating a large dataset of automatically labeled spectra would be easy. However, it may not be as accurate as training on real spectra. Okay, so in this section, I'll just give a brief overview of the various methods and functions contained within MCALF, and we'll take a more detailed look at some of these that are more important for working with it. So MCALF has four main sub-packages. It's got models, profiles, visualization, and utilities stuff. So the most important of these are models and visualizations. I will have a look at these in more detail in the next few slides. The other sub-packages are profiles and utils. Profiles is useful if you're building a model. It contains the various different functions like the void functions, Gaussian functions, that can be useful when selecting how you want to build a model based on the classification that the spectrum was assigned. Utils then includes various bits and pieces that are useful behind the scenes if you're creating your own model. They're also useful if you are inputting data into MCALF. You can do some pre-processing of spectra, and then it's also useful for the output data, like you can average throughout time and space, for example, with your velocities. So to use a model, first of all, you initialize the model class. You then load an array of spectra into the model. Then you can train the classifier using the train and test methods. Once the neural network is trained, you can then call the fit method and tell it a particular range of data that you want it to fit. You can also specify the number of processing pools that you want it to fit it over. So if you have a lot of processors, you can basically divide it all out equally because each spectrum is fitted in parallel. So this fit method will return a list of objects each object representing one particular pixel. You then merge all of these pixels into like a two-dimensional object, this fit results object, so that you're better able to see the sort of spatial distribution of velocities and the parameters that you fitted, as well as the classifications that each spectrum was assigned. You can then call the save method on this object, and it saves your results as a fits file. So these are the four classes that are contained within the models subpackage. The model, so you'll be working directly with something like IBIS 8542 model or another similar model if you want to, define your own model. And this model is based upon the model base class. Anything that can be abstracted out of the IBIS 8542 model or any, final model that you'll be using is sort of put into this model base so that you can then build new models from the model base and only implement the things that need to be for the specific data set. If you call the fit method on a model, it will return a list of fit result objects. You can then create a fit results object and append lots of fit result objects to that. So this is just a brief overview of how you would go about creating a new model for whatever you want, like a new data set, or you could even use MCALF to fit stuff to, say, a time series. It doesn't necessarily have to be wavelengths. So you create a new class that's based on model base, and then all you have to do is define the underscore fit method. This method accepts a one spectrum, a one-dimensional list of numbers, a classification, and a spectrum index. All of these are inputted by MCALF, so if you load in your data, it will automatically pass through the index of the spectrum in that data set, and it will find the classification and send that through as well. So then all you have to do inside that is define however you want to fit the data based on the classification. So you can use the classification to sort of change about stuff. And then what you do is you just return a fit result object. This is useful, like if you want to create your own model that's, you can get other people then to use, and it's all user friendly. So all they have to do is just call a various small list of methods on that and get their fit results. And then optionally, you can define a plot method if you want to sort of support, plotting of the results of a particular fit or plotting individual spectra that are contained in your model. And then the other main package is the visualization subpackage. So this basically includes lots of different visualization functions that are all particularly designed for working with the type of data that MCALF uses. So there's various stuff for working with classifications, it's able to group different classifications together, plot them, plot the sort of map of, spatial distribution of stuff and various abundances of each of the classifications. It then has stuff working with spectra. It's able to plot spectra. And then it has a function then for plotting a two-dimensional velocity map. You'll see some of these more later in the example that I'll show you. There's also an example gallery for visualization, and you can sort of see how all these integrate with matplotlib. Like they're all fully customizable. You can change the titles, and axes labels, and such. So MCALF has got two publications. We have a publication that's based on the method that I presented earlier. It's in the Philosophical Transactions of the Royal Society A. And then we also have a paper in the Journal of Open Source Software, JOSS. And we have a few more papers coming up soon of people using MCALF for their own research. Okay, so I'll now take you through something from the example gallery. This is sort of showing you how you can take a real data set, a sort of subset of our IBIS data set, and apply MCALF to that and do various different visualizations. This should hopefully give you a better idea of how MCALF works in practice. So I will show you that now. Okay, so this is the MCALF documentation website. It contains various different stuff on how MCALF works as well, you know, the API documentation. But we'll here look at example gallery. So it has various different examples for visualization as well as models. It's got two for models. The first is looking at real data. The second is simulated data. They're both very similar, but we'll look at the first one, which is using real data. And this is it. Now this can be downloaded as a Jupyter Notebook, which I have done, and I will take it through to here. So first of all, what you would do is you would install MCALF, pip install MCALF. It then quickly just installs it based on compiled wheels. So that's installed. So then we'll just download some of the sample data that's hosted in GitHub currently. That's done. And then we'll just load it in. So what we've downloaded is we've downloaded the file wavelengths.txt, which is the wavelengths of each of the that are included in our data set. Then there's spectra.fits, which is our two-dimensional image, you know, with each spectrum, you know, with an X and a Y location of a spectrum going down. And then we've got training data, which is basically indices in that their spectra.fits file corresponding to actual classifications. And we'll use that for training. And you can see we have 27 wavelengths. And we have a 60 by 50 image. And here's just a quick plot showing the blue wing and the line core intensity values for this data set. So the way that this class is implemented currently, it assumes that for, you know, minus infinity to positive infinity along the wavelength axis, it sort of goes to zero, the intensity goes to zero. This is to basically reduce sort of the amount of parameters we have to fit. But I found that this was an easy sort of thing that you could work out anyway by averaging out into the wings. So here what we do is we just average the first 4 points of each spectrum, and then we'll pass this into MCALF, and then MCALF will know to subtract this array from all of the spectra before it fits it. So everything starts at 0 and goes up, or it'll go down, or, you know, if it contains multiple spectra. So that's that generated. Okay, now this is the main part. This is where we import the models from MCALF and we initialize the model object. Into this, we pass the original wavelength. So this is the wavelengths from the data set that we're going to be working with. Now, these wavelengths don't actually have to be equidistant from each other. However, inside MCALF, it will like reinterpolate all the spectra so that they're all equally spaced apart. And we can also specify the wavelength step between all of these. However, here we're just using the default value. Now, a lot of other parameters can be changed in here, like the various bounds and such of the fitting method, but we can just use the default value here. It also supports loading in a configuration file that's easy to share about with other people, so that you can just, you know, load in a simple file without having to like type in or copy and paste all the parameters into your Python script. And then this random state, I'll talk about this more later, but this is just to create a reproducible neural network that controls the randomness in the training process. So once the model is initialized, we then load the background that we discussed earlier, and we also load the array of spectra taken from the IBIS instrument. For the second argument to these methods, we label each of the dimensions. So, you know, there's wavelength, and then row, then column. So this means that the user doesn't have to worry about transposing all of their data to be in the right shape. All they have to do is just tell MCALF, this is how each of the axes are labeled. And then MCALF internally will transpose it before using it. So I'll run that. Okay. So, right, we're on to now the classifier. So the classifier is stored inside the .neural network attribute. Now, although it's called .neural network, the classifier doesn't actually have to be a neural network. It could be anything. It just has to support the same methods, the same key methods as scikit-learn's MPL classifier. So you can see here we're doing a grid search. So we're trying out various different parameters on the MPL classifier. And then what it will do is it will select the best one. The next step is then to load in the training set that we downloaded earlier. You don't need to worry about this too much. This is just basically loading in the indices, selecting the indices from the data set, and then creating a corresponding list of classifications for each of them. And here is just plotting each of these. So you can see the different classifications all grouped together. So this is what we're going to be training and testing the neural network using. This is our labeled set of spectra. We can then call the train method on our model to train the neural network. We then provide it a list of spectra and then corresponding classifications. We then take a different set of spectra along with their corresponding classifications and see how well it's able to reproduce the classifications that we tell it it should have. So we see here there's various statistics generated. The table below is from scikit-learn. The table above is one that I've implemented in the test method. It's sort of handy for seeing how far away each class is from another class. So the deviation, we see that these are all very low. So if one of these was higher, say if that was, say if 2 was say 1.1, it would mean that on average, anything like wrongly classified is like one whole classification away. So since that's so low, it means anything that's sort of off isn't off by a lot. Okay, so usually in MCALF, what we'll be doing is it'll be like classifying the spectrum behind the scenes because we're interested in fitting a model and extracting velocities from the results of that fit. However, we can just extract the classification. So we can just tell it, go classify this range of data, and then just tell us what the classifications are. You know, that could be useful as well. So that's easy enough to run with the classify spectra method. So you then just tell it the data range, you know, what rows and columns of the loaded spectra that we want to classify. And then in the visualization package, we then have a function called plot class method. And this basically takes the sort of thing that we've just generated previously, that classifications variable, and it plots it. So this is good. Then we can see the spatial distribution of all of our spectra. We can see, you know, down here, we've got, you know, absorption stuff happening. And up here at the top, it's sort of like emission. And yes, so this is a matplotlib object. So it's all fully customizable. You can, you know, change axes labels and such and combine multiple ones together. Okay, so a bit about reproducible classifiers. So as I showed earlier, there was that random state integer that could be set. So that's just to control the randomness. So when it trains, it'll have various random processes that it does when, like, you know, shuffling the data set and stuff like that. If you just set that random state, it should then keep all those the same. So you should, every time you train the neural network, you'll always get the same, you know, weights and biases out at the end. There's also the option to use the pickle package, you know, from Python. So you can basically dump the model.neural network object into a pickle file. And then later you can then open that file again and load it back into the model.neural network. Now, if you do that, you don't have to worry then about, you know, generating, like loading in all of your training data and calling the train method and the test method, because you've done all that already and you can just reuse the previously trained network. However, you do need to be careful that you're using the same version of scikit-learn and its dependencies, as there may be issues with compatibility between versions. And as you can see, these are all the same as before after we've saved it and reloaded it from file. Okay, now the main part then is fitting the spectrum. To fit, all we do is we call the fit method on the model. We give it a particular row and column range that we want to fit. So typically you might want to do the whole range, or you might just want to select a subset of your data when you're doing some initial testing. You can then say the number of processing pools you want to use. Now on my own laptop, I found that this particular call would take about 10 minutes to run. So just for speed, there is, earlier we downloaded a file, results.fits, and this basically contains all of the results. And basically this cell, it's just like loading it back in. So we can just now pretend that we have run this and it has created this results_list variable. And yes, we can see that this is a list of fit result objects. So, and each of those objects corresponds to one individual pixel. What we then want to do to sort of see the spatial distribution of everything, we want to merge them all into a two-dimensional grid. So first of all, what we do is we initialize a fit results object. We tell it the number of rows and columns that our data set has, as well as the maximum number of parameters that we're going to fit to our data. Once that's initialized, we can then loop through our list of results and append each of them to the results object. You can then extract various different arrays from this, the parameters, the classifications and such. But a handy one is the save method, which will then export all of that to a fits file. And we can then load that back in and see what that contains. So you can see it contains parameters, classifications, profile, success. So that's like whether or not, it was able to successfully fit a spectrum. Chi-squared, which can give you a rough estimate of how well it's fitting, as well as the active line of sight velocities and the quiescent line of sight velocities. So you can select individual fits for individual spectra from what we've done there. So we select the 0, so we select the first fit. We can then pass that into the model.plot method, and it will then plot the result of the fit. So we can see the blue line is our raw data, and then it overplots the fitted profile, as well as some vertical lines showing the stationary line core and the absorption line core. If this was spectrum contained both absorption and emission, we would then also see other lines for the emission, as well as a combined profile for both added together. And here's just basically the matplotlib integration. We can call the velocities method, and we can extract the type of velocity, so quiescent, active. We can then define a mask. So you can see here, we mask out the umbra, and then we can get it to draw a line around there. So we just create a mask. We just define it to be 1100 intensity. And then we just pass it in as the umbra mask parameter. And we can see, yep, these are plotted together, so side by side using the various matplotlib features. So that is that. I will go back to the presentation now. Right. Okay, so I'll now briefly go over some of the infrastructure behind MCALF, the various DevOps stuff, methods and services that we're using. So testing, publishing, and documentation. Okay, so testing. So for our testing, we use PyTest. It does unit tests. We have 94% coverage of our code base. To generate coverage, we use PyTest's pytest-cov plugin. The coverage data is then sent to CodeCov to allow us to then track inside of GitHub whether or not any new code or old updates to the code are affecting the coverage positively or negatively. And then since we've got a large visualizations package, we sort of needed a way to sort of test that any changes we make or any changes actually that other packages make don't mean then that it breaks visually what our plots look like. So because something could break where it doesn't actually raise any errors, but something might be flipped around or the color is changed, and we'd want to know about that. So we use Matplotlib's PyTest plugin in order to automatically inspect the plots visually to check for stuff like that. The tests are run inside talks. So we can create some different environments. So we can control which version of Python we're using and also the versions of MCALF dependencies that we're using. This would allow us then to see that, if another package, a new version of another package then breaks something, or if an old version is no longer supported, it allows us to see all of that and make adjustments. And then these are all run inside Microsoft Azure pipeline. So basically what we're doing is we're different environments. So we've got Linux, Mac OS, Windows. We're sort of running across all these different operating systems. It's a lot. We probably don't need to do this much testing. It was sort of, I wanted to learn about testing. So I sort of probably did too much testing, but can you really have too much testing? I don't know, but yeah, so for this, we're using the Azure Pipelines templates provided by Open Astronomy. These templates were absolutely amazing for quickly being able to generate a configuration file for Azure Pipelines. You basically can just specify the names of the various TOX environments that you want to test, and you don't have to worry about all of the other stuff you need to do to get it all working. And then we have publishing. So MCALF is available through both pip and conda. Now, to get it available in pip, we submit it to the Python package index. This is also done automatically using Open Astronomy's Azure Pipelines template. So anytime we make a commit that is tagged with a particular version, it will then trigger that particular template to run, and it will then send it to Python package index. Once a new version is available in the Python package index, Conda Forge realizes that, and it then opens a pull request for the developers of MCALF to review. Once we review that and we see that our tests have all passed for Conda, we can then merge that in, and then the new version will be available through Conda also. And then we also use Zenodo. So Zenodo lets us create a DOI for each specific package version. This makes it good for, it allows users of MCALF to reference a specific version that they use. So it makes it easier to reproduce their results. And then we have documentation. So our documentation is hosted on Read the Docs. We generate it automatically using Sphinx. We're using the Sphinx Gallery plugin. That's the thing I showed earlier. Here, it generates all of these gallery stuff, which is quite nice. What I like about this as well is if you look into the code reference and you say go to a particular function, it then will show you the examples here. For example, plot a fitted spectrum. So it shows you the examples automatically where it uses that particular function or method, which is very nice. If someone's reading through the API documentation and wants to just actually see an example of this being used. And then to further speed up the whole process of generating documentation, we use AstroPy's Sphinx AutoMod API plugin, and it will basically just automatically generate lists of methods and functions so that you don't have to type them all in by yourself. Although I'm actually using a slightly modified version of that. So I've submitted a pull request to that package. And what it does is it implements a new feature where it will also document lists of underscore methods that say start with underscores. This was particularly for the underscore fit method that has to be implemented if you're creating a new class. I thought that this would be handy for doing developer documentation where developers might want to know more about the private methods that a class implements. Okay, so next is just the future of MCALF. Like I've got a lot of stuff that I would like to develop and improve MCALF with, stuff about managing the data. I would like some way to reload the exported data. So currently, once it exports stuff to a FITS file, it's you can't really load it back in that easily. So that might be handy if you want to do some more replotting of previously fit spectra, and maybe doing some more inspecting and calculating various different numbers from that. And then of course there's various internal changes that I could make, to make it more efficient and make it easier for people to implement new features. And then other stuff like creating a library of trained classifiers so that the time consuming part is generating your training data. So it'd be quite handy if someone was able to download MCALF and select a pre-trained classifier, for whatever data set they're using, so that they don't have to, go through and train everything. And then, create more examples and stuff. I would like to create more model classes because currently we only have one model class. So it's only really set up for one particular data set. So it would be quite nice to have more data sets in there, which I plan to add as I work with new data sets. I will create new models to include. Or even experiment with different fitting methods, because each class can have a different fitting method implemented on it. So we could just create a new class that implements it in a slightly different way to see how that works compared to other ones. Yeah, and of course then support other people who want to use the package. That's something I would like to do. Help them with the research and helping them, add new features into the package. That would be great. Yeah, so thank you everyone for listening to me talk about MCALF today. I'd be happy to answer any questions you may have.